Okay. All right. Right. Good. These crazy people. Okay. Indiana Jones reference. There you go, for free. All right. But this is the game. We're going to be thinking about a couple of pieces. One is basically when you have these things specified, right? The number of nodes and then the number of edges, and the nodes are labeled. It's important, right? So they've got names. Or it's, node A, B, C, D, whatever you like. And then we get into trouble because our alphabet runs out. They're labeled, and so the links aren't labeled though, so that's important. But we're going to think about all possible configurations. All right, we're going to have a box of them, and we're going to pull one out at a time and then look at it and so on. And then the game will be sort of just to move out from that. So we'll be interested in a really beautiful part of all of this is bipartite structures, right? So we have two kinds of things, maybe boards and directors, or actors and movies. And you think about the degree of randomness involved in the connections of those things. But we can construct random ones. So this is something obviously we're not going to do this, but you could cut it out. The idea here is this is actually every possible network for just 3 nodes, right? So we can have no one has any friends, and then the fully connected one over here, and each one has probability, right, equal probability. So that's a fun thing to make. But what we're going to do is be in a category where we know the number of edges. So it might be we're restricted to these 3 sides here, or these 3, right, where there's 1 edge, and in this case, 2 edges. So that's not very exciting, but of course we look for a large N, and then we end up with it becomes hard to tell that we don't have a polyhedron. We have a polyhedron. We in fact have a ball. That was in Gravity Falls, right? The infinity-sided dice. Yeah. Okay. Which is a bit like Borges' Book of Sands, right? So you're always going to get something different. Okay, so basic things. So we're going to have a set of networks. They're labeled nodes, M edges, and what we'll call a standard random network, or what will be often referred to in the literature by many people as an Edish-Rennie random network, because of the humans involved, will be one of these networks. So each one is equally probable, right? So this is just the basis, this is where we start from. And the number of, that little thing I just showed you that you could roll, that 8-sided die, that's fun. But it really, when you think about networks in general, like the really important pieces are the number of nodes and the number of edges, right? So if you've got a real one and you want to compare it to some artificial ones, you really need to hold those things constant or do some smart scaling, right? So, okay, ER graphs, all right? Equiprobability, equi-things, good assumptions. Physics is full of it. Lots of equipartitioning of things. All right, so number of possible edges goes from 0, if we can have 0 friends, and then n choose 2, where everyone is connected to everyone else. And we're usually interested in the sparse ones, fully connected. And then the number of networks with n labeled nodes grows enormously, right? So there are n choose 2 possible edges, and they could be either on or off. So we have 2 states for each possible edge, and then we multiply them all together. Again, these are labeled graphs, right? You get into all sorts of fun if you don't do that, right? If you start to think about isomorphisms, that's not what we're doing. And it's very beautiful. Okay, and then you can play around with this a little bit. So this is great, like e to the n squared, which is, kaboosh. It's the technical term. Okay, so if we have m edges, then there are n choose 2 places, right? So there are n choose 2 possible edges. You have m that you're going to place down. So this is how many we have to choose from. So we have n choose 2, choose m. And that's a little thing you can mess around with, Stirling's approximation and so on, some factorials, and figure out how that thing grows, and it grows nastily, right? This is basically an n squared choose m. So, lots of possible networks. So that's this. So we've got this box here, and every network you can think of, and these are unlabeled edges and so on. So we're not worried about the node size or whatever and weights and things. But imagine you have some real network, which is been stripped of possible information, but it's like that. What's the chance that you pull that one out of a box that has the right number of nodes and the right number of edges written on it, right? So we've got these set of boxes. N equals 7, m equals 4, or n equals 1,000,000, and m equals 100,000. You have your real one over here, and you say, okay, what's the chance that I get something like that, right? Yeah. And we know from earlier stuff in Pox, right, a lot of the real ones are pretty structured, right? They're power law size distributions for degree. Depends who you ask on Twitter, I suppose, but their scale, they're heavy-tailed distributions, right? Academics are such fun people. Okay, so of course, yes, this big piece. The real world networks that we often think about, they're sparse, right? And usually that's based in links being costly, but also even if they weren't, it's useful to have sparseness actually, because if you're all connected to everything else, then everything kind of explodes. You have to continually make choices on how to make the network function. All right, so let's build them. So N and M, we've got a couple of ways to do this. And I know this is a reminder of sorts, but we'll connect it to contagion at the end, which is very important. And then, as I said, it's a nice setup. Okay, so, and you're welcome to gesticulate for questions, and I'll try to answer them. Or find a previous version of me that knows what was going on. Okay. That's true. My lectures one day could be just I'll just Google search for, someone else's videos, let's be honest. All right, so we're going to have probabilistic methods. So the first one will be, and this is a nice thing theoretically, where we will just, usually theoretical, we will just say, okay, we're going to have some probability P, and we'll we'll go to every pair, and then just sort of flip this coin that's P1 minus P. We could have our M links, and then we have our nodes laid out, and then we choose pairs at random, and then we put them down. And we have to choose, right, so they've got these empty spaces. We choose without replacement, right? So we have to, once it's filled in, we can't add another one there. If it's a pretty sparse one, then that's not too bad. You can just sort of add edges, and if you find one's already been added, you just sort of go back and do it again. So this is good for theoretical stuff, and that's this story here, right? So for how to do this one. So we're going to randomly choose a pair of nodes, I and j, put an edge down, and then we just keep going until we've allocated all of them. This is great if there are small numbers. For large n, these are going to end up being basically the same. Of course, if there's already an edge, as I said, if there's already an edge between them, you just start again. You just forget that effort, right? And that'll be fine if it's sparse. Cool. Okay. And of course, now it took a long time, to be honest, but things like NetworkX and GraphTool have these things built in. It's kind of amazing, actually, how long all that took. I mean, I wrote all my little versions in C ages ago and sort of made them work with MATLAB. And that was good, but none of these things. I guess GitHub really didn't exist. People weren't sharing things that well or as easily as they can now. I mean, you could put stuff up, but we didn't really get packages for a while that people could play with. Anyway, so that's good. But they are fun problems to they're good coding problems. They are good things to think about. All right. So we're going to end up actually with a probabilistic number of edges in that first case because we're adding things probabilistically, and so there are n choose 2 possible links, and we're going to get this fraction p of them realized, and this is of course this n choose 2 is a half n minus 1, so that's what we have there. So very simple thing. The expected average degree, so we'll need this little connection. These pieces here are quite important. So this is the average degree, right? We always use K. That's pretty standard in at least the complex networks literature. There's no great reason for it, but average degree K will be 2 times the expected number of edges divided by n. So the 2 is here because let's randomly choose something that doesn't work. Oh. Right, this is, just to remind you, this is boop, boop. Yeah. Right, so an edge, we're going to break it into 2 pieces. So in terms of degree, right, this has got a number of other friends, right? Each one of these counts as 2, right? So we get 2 edges, incident edges, per edge, right? Right? That's fine. Okay. So we have to count, if we're going to find the average number of friends a node has, we have to double the number of edges and divide by the total number of nodes. Okay? Right? Just the 2. And then if we've got our probabilistic method, right, we're just going to stick that result in there. We have 2 over n. This is not a complicated thing. The 2's cancel, the n's cancel, and we get the right thing. So p times n minus 1. So from a node's point of view, right, if you think of it from a node-centric point of view, it's always best to think of network stuff from edge point of view once we get in this kind of world we're in now, I suppose. So you've got a node. It has n minus 1 other friends, potentially. And so we're going to randomly attempt to connect them. And we've got a probability p. Right? So this is the expected number of other friends that a node will have. So we get to it in 2 ways. We can argue for it directly, right? So p times n minus 1. What it should be, of course. And so often we're going to say we need this specified, average degree. We want everyone to have, on average, 4.5 friends. And so if that's the case, then we're going to keep this fixed, and we'll often think about networks as n becomes large. We want to sort of consider that kind of family of networks. Then p has to decrease, right? So our probability of connection has to go down. And in fact, we'll go to 0, right? If we want to end up with a finite number of friends, average number of friends. Okay, so that's just a little important detail, and it's why you end up with ultimately Poisson degree distributions instead of Gaussian ones. It can't be Gaussian because it just doesn't make any sense anyway, but you sort of, right, because of negative things, but you might think it might be pretty much more like a normal, but it's actually Poisson, and that's the part of it. So, okay, visual examples, just so we're there. So we've got 500 nodes, and this is using I should try NetworkX or something for this. This is an old one. So let's see. So 500, we're going to vary m, number of edges from 100 to 1,000. So 2 times m divided by n, right? That's our little simple calculation, right? Average degree. Wow. Dead. Also dead. Average degree is 2m over n. So yes, we go from 100 to 1,000, so we're going to double this thing. So it's going to be 200 over 500, 2,000 over 500. So we're going to have an average degree going from 0.4 to 4. And as you may recall, if you've been in PUCs before, 1 is the big deal here, right, for random networks. So it's a good anchoring. So we're going to look at the full network plus the largest component. So this is sweeping across these average degrees. So again, 0.4, tightening up around 1 just because there's more interesting stuff there, 0.8, 0.92, 0.96, and this is 1. Of course, it's just one instance for each of these, and it's only 500, but which is not a lot of, it's not a big network by any stretch of the imagination. Let's see. So you see, a lot of isolates here, right? So nodes that have no friends, and then these are all little pairs, and then there are a couple of triples in here. This one looks like it's 1, 2, 3, 4, 5. So that's the biggest one in there. Certainly no cycles. Right? You could have some with some randomness, but no cycles here. So you start to get these tree-like structures connecting, and for random networks, the key thing for a lot of the analytics will be that locally everything is a branching network structure. So even though as we get to hairballs, it's still going to be all about branching network structures. All right, which is quite fantastic. Calculations are really beautiful. We will get to generating functions, which will warm everyone's heart. It is quite majestic. I mean, it has power, but you don't have to use it everywhere. Okay, so let's see. So we get to here, and this is an interesting case. It's starting to get a little nutty, and that's certainly true here. And we're only a little bit above 1. Again, 1 instance. But the singletons are dying out, right? The number of nodes that just have one friend. There are just a few of them sort of scattered here. Right, so a big issue is how do you display these things, which are obviously much higher dimensions and high dimensional structures in 2 dimensions, and that is always a bit of a game, but this is just sort of smushed. Do you get this sort of? Yeah, at some point. Yes, and there's some really nice transitions in terms of when you get giant components. All those things are there too, right? So you get the same kind of story, like whether the realized one will have a giant component. And we have to think about the things we're trying to create. But usually you're inducing the network, right? So there are these 2 groups, and they what we're going to do is project, right? So if you share a category, then you're friends, right? So we'll do that sort of thing. The really interesting things to play around with there are just like moving it a little bit, where you fill in the network a little bit. You sort of say, you start to add some extra connections, and that changes everything. But just small deviations away from these models are quite valuable. But let's see. I mean, I know you've asked probably not what I've. Yeah. We'll get to that one. And maybe I should make some pictures for it. Yes, okay. Okay, so these are the largest components. So this one had 7 in it. And again, it's just a random instance of it. And we start to see a loop here. That seems to have sort of disappeared in this one, which is we didn't see one in this example. Loops. And the loops are long, right? So they're relatively long. Again, not a very big network in the first place, but there aren't any triangles here, right? Because that's going to be a harder thing to get out of just a random wiring. And we really have, by even just an average degree of 4, this is a really an important thing to sort of understand. The average degree of 4, which is not many, we've certainly got a hairball, right? Which is, a mess to try and put onto a page at this point. This one, we could imagine trying to tease it apart, but, nasty. So average degree of 4 is pretty rough. All right. So that's the largest component. But this is just a sort of, this is an entry into thinking about things like disease spreading and so on. There can be a dynamic underneath how these networks are created, or you might be looking at an outbreak, after the fact, and this is something where it went kablooey, right? This is bad. If you have some way of controlling connections, like how people interact, then you want the big deal will be to move the system below this 1 here, because now you do not have a giant component, right? So we'll talk about a giant component. That means the largest connected group in the subnetwork. And it will be giant if we can see it from space, basically, right? So if it takes up a macroscopic fraction of the whole network. All right. So these are just a whole bunch now for just average degree 1, right? So this is a critical point for this system. Critical points are fickle things, especially at low numbers. You know, if we took it to an infinite limit, they would all do the same thing. But at 1, you get this kind of, the largest component tends to be a fractally, tendrily thing. Is that on the next one? Yeah. So it tends to be, and this is true of, you know, percolation type things, all sorts of other structures where at the critical point you tend to get a sort of a fractal thing. It doesn't take up the whole space. Yeah, so spidery, webbery things. And then, right, as soon as we sort of move above, right, we tune it so the average degree is a little bit higher, then we'll start to see these loops. I mean, we'll see some, of course, anyway, but this is, again, a finite size effect. So, okay, it's sort of a feel for these things. All right, let's rampage through. All right, so here's the, you know, a big piece. So S1, so this is a fractional size of, so S for size, fractional size of the largest component. So we're going to take all the components, connected components in these networks, sort them out by size, right, just as we would with, say, rank ordering for Zipf's law. And the largest one, its fractional size, right, 1 is the maximum, as this is the average degree of these pure random networks. As we tune up to 1, the largest one is, you know, you can't see it, right? From a long way away, infinite network getting bigger and bigger, it's just going to be a bunch of like little speckles. There'll be little groups connected together. And as you kind of approach here, the largest one sort of grows logarithmically with n. So it grows, but it's very, very slow. And then suddenly when you get here, you have a fractal kind of largest component. And then suddenly, boom, once you're above it, you actually have a clump that is some non-zero fraction. So this is a really important piece here. And it is a continuous phase transition, right? There's a discontinuity in the derivative here. It's a continuous phase transition. There's no wild jumps. There are, you know, ways of looking at networks so that you get, you know, as you cross here, suddenly you get boom. And it's called explosive percolation, I think, which sounds wrong. It's Raisa de Souza's work, I think. So let me find that. So this is a big deal, all right? So as I said, average degree 4, almost everyone is in the largest component, right? So we don't have to go much further out here before everyone is on the same part of the same team. Okay, cool. So we'll use this little piece later on. And so, you know, basic question is, can we extract this, right? Can we get this transition? So from a disease point of view, can you tell if something's going to take off or not? And then what do you need to do to change the system to get it into this category? So that's just you know, like a binary thing. Will spread, won't spread. So it's a transition. And then if it does, you know, what's the probability it takes off, and then what's the final size if it does? It's a sequence of questions, which surprisingly hard to answer some of those pieces, depending on the network we're thinking about. Okay, clustering. Okay, this connects back to what I said before, that locally all of these structures are branching networks. I need to drink a lot more. Okay, so this is the Newman's clustering coefficient. So this is the number of triangles divided by the number of triples with a 3 to clean up the fact that each triangle closes a triple. And it can be interpreted very nicely in this way. We have a node, has 2 friends. What's the probability that they are connected? And that's our C2, if we average over everything. All right, so if we're randomly making these things, then it's going to be that, and we're using that first construction method, C2 has to be P, right? It just has to be the probability that you connected these, because it's independent of these guys, right? So, and as we saw for large n, right, we want to have an average degree that remains the same. So as we look up, as we go to larger and larger networks, then this P goes to 0 as 1 over n. So the number of, the chance that you even see a triangle goes to 0. And you'll start to see that if you sort of move further out and ask the same questions, right? This one does have friends, right? There's an infinite number of others to connect to, or a growing number to connect to. So it's going to be connected on average to some of them. Be a little bit careful about the average number of friends this one will have. We'll get to that. But this will start to look more like a tree, right? And the loops that you get will be long. The cycles will be long cycles. So that's just a hard thing to deal with. Okay, so, right. Okay, and that is the story. So locally, these things look like branching networks, which is going to help for our calculations for how things spread and so on. And the sneaky thing that people have been able to do over the years, and we'll see that in fact it's better to eventually really dive into the heart of these things that have loops and so on, is to say, let's take the giant component and just leave that by itself, and we'll examine all of the other ones. And because they're finite, then they will actually be pure branching networks. There's no chance that they have some loops inside them. And we can study them exhaustively, and then we'll say everything, so it's like a negative space thing, right? We'll say everything about everything that is not the giant component, and then we can talk about what the giant, what its size is in particular. So that's some trickery, but we'll see that in fact you can go right into the giant component, which is pretty spectacular. All right, pure branching networks, yes. No small loops. All right, that's good to know. Okay. So we're just getting ourselves back into random networks so we can build on this. Degree distributions, right, beautiful thing. Okay, so I guess I started this by saying that n and m, right, the number of nodes and the number of edges, hugely important things, got to set them up. And then the next big part is really the degree distribution, which, if you had a temporal dynamic network, would be a contact rate type thing, various permutations of this, but degree distribution, we're thinking about static networks. All right, so how do we build this, right? So we're going to choose that method, that first method for constructing networks. So one node has n-1 choose k. That's how many ways you can choose k other friends. And each of those connections, you'd have to turn them on with probably p, and all of the other ones would have to fail with probably 1 minus p. And so we can put it together like this. We have a binomial distribution. So probably thinking about one node, and therefore all nodes, probably that a node has a degree k, given that we're in a network of size n, and there's a connection probably of p. So there are n-1 other friends that a node has potentially. We want to choose k of them, so that's how many different arrangements we can have. So this is counting. And then for each one of those, we have to have this happen. We have to have the k of them be, the coins we flip, they have to switch on, and the coins we flip for the others have to turn off. And the others, there are n-1 total friends minus k, right? These things add up to. Okay. All right, so it's a binomial distribution. And then you can mess with this, right? And look at the limit as n goes to infinity. And the piece we'll need to do in here is to replace p here by the right thing, which is average degree divided by n-1. Right? Let me write that down. Where's my thing? Right, so this is just a crucial thing. So we had average, also sad. I lost it. Average degree is also p n-1 in this construction method, so we can replace p with this. Okay. Right, and we're going to fix this. We want to say, average degree is 7, and then look at the limit as n goes to infinity. And if you do that, you get a, right, you'd think you'd end up with a normal distribution because this is sort of what happens a lot, but that's not the right game. So this is what I've been saying. So it's roughly going as p times n. And if you do this limit, Okay, so this is what we had before. This is going to, and we're right, so this is from the factorial out the front. This is the classic, 1 plus blob divided by n to the n. That ends up as scaling as e to the blob, right? Which you can always reassure yourself with L'Hopital's rule. It's very nice. And this object here, right, so this is our average. The notation is not ideal. Sometimes people use just a completely different thing here like z, but this is the average degree, these are constants, and this is a Poisson distribution, right? Which is the right kind of thing, right? It's a distribution of a discrete variable, 0, 1, 2, 3. It's a fine distribution. It's been used for lots of things, right? Things like, right, so it's about how many things happen in a given time period, given a rate of occurrence, right? And things are, otherwise random. And it does pretty well for some strange things. Okay, yeah. So actuarial people have been quite fond of this for a long time. But it appears here very naturally. It's a quite well-constrained distribution, as it dies away fast. There's no heavy tail or anything like this. I mean, the point is that for random networks, you have sort of a typical number of friends, and there's some variation around it. But that variation is quite small, and we'll get to this. But the variance for a Poisson is the same as the mean, right? Which is just a thing. So it means that the standard deviation is the square root of the mean. And so that means you've got something like, so say we've got our Poisson is out here, then the typical width of this thing, so this is our mu, the typical width of this thing, 2 sigma, is square root of mu. So from a long way away, this starts to look pretty much like a spike, right? There's not a lot of room around the thing. Okay, so this is the point, this is the variance. You can go through and compute it. So it's not shown here, but the second moment turns out to be the first moment squared plus the first moment. And then if we compute the variance, we get this result here, right? So that the variance is actually the first moment. So that's kind of a nice thing. And it leads to some odd things in the way people have understood how spreading works, because there's a very peculiar property of the Poisson distribution. We'll get to that again. Anyway, that's a good thing to remember right now. So configuration model. So this is very important. Again, something that was sort of developed in different ways, but Mark Newman did a lot of work here to sort of bring it into people's vision. So configuration model, or we can just say arbitrary degree distribution. Often we sort of use those words. And so we could generalize this construction, right? We're sort of really, well, let me just say this again. So we've got, let me go back here. So what all of this means is if we go to this box and we've got a large N, a large M, and we reach in, we pull out a network, and we do that over and over again, we'll always get one with a Poisson degree distribution, basically, right? We'll always get them. So, but we know the world is full of networks that, in fact, do not have that degree distribution. And in truth, I don't think anyone's ever really seen one. Like in a real world, large kind of messy network story, someone's, here's a network, of larks who talk to each other, or, porcupine somethings, phone calls. While Poisson distributions, as we sort of talked about, they appear a lot. That's a really natural kind of thing. In terms of Poisson degree distributions, I don't think anyone's ever really found one in the wild. So that's really weird, right? So the thing that we make this kind of randomness is a great thing, and usually, gets us a long way in describing the real world. A lot of the work we do, I think, in some ways can be thought of as like removing all the randomness until you find the structure, the shape of something. It's like sculpture. Anyway, you reach in this box, you pull out something that you don't see in the real world. And you do it over and over again, and you're like, what's wrong with this? This is crazy. So these are things that live in our heads, and we made them up. And nature doesn't do that. Nature makes things, right? They grow. And so these aren't easy to grow. And there are some nice thoughts about how you might grow them, but we didn't grow them, right? Callaway paper, yes. And pretty, so sort of naive models of how to grow a kind of random network will actually give you something that departs from these things. It's sort of hard to manufacture. All right, so that's all fine. I mean, we understand these things well, and they have a couple of really incredibly important things, like the phase transition story for the giant component. That's a huge deal. Like, that's an essential story of networks in general and how things spread and so on. That's an incredibly important thing. It's just not, it doesn't exactly fit the real world though. All right, so so these standard random, they have a Poisson ones, but we'd like to allow for arbitrary degree distributions. And so we can just do this in a couple of ways. One is to say, well, let's sort of generalize the way we build things. Let's give these nodes weights, and then we'll make the probability that we connect two nodes, have be a product of these two weights. And if we choose this weight distribution in the right way, then we can kind of really control the outcome. And so if all the weights were, equal, then we'd be back to where we were, right? We'd be making these Poisson ones again. But so we're going to step away from constructing these things. It'll be actually more interesting to take real ones and mess with them, and also just say, this thing has this degree distribution theoretically, and then let's see what that means, right? If we're going to spread things and so on. Yeah. And of course, this is something. The power law size distributions or the heavy tail distributions, that's something that's being examined to pieces now. Obviously still people still have to tweet about it, but it's it's the rich get richer mechanism, which we've talked about a lot. Okay. Big deal. I'm pretty sure Marx understood that actually. That's why we need taxation. Okay, all right. Actually, in that paper shredder discussion group, we looked at a paper that basically made that point. That said, look at all these rich get richer mechanisms. Didn't quite, right. Not quite a revolutionary document. Okay, let's see. So, so these are ones that have power law degree distributions, right? So these are going to be quite different. They're random networks again, though. They're random networks. We've just wired them up randomly and so on, right? Good. Need to talk a little faster. These are the largest components. So these things, now it's a completely different game, right? And these are much more like real-world networks, or many classes of real-world networks. Doesn't always pop out the right way, but there are these centralized hubs that have many, many friends, and some of those will have many, many friends and so on. So you start to see kind of hierarchical structures. The average degree is quite low, right? There's nothing huge about these things. But you also see, because it's one of these, it's a rich get richer thing, you have the very wealthy in the middle in terms of friends, and then you have the serfs out here with the one friend, right? Yeah. What's the Ron Swanson line, right? Capitalism, isn't it? It's a method for sorting out who is rich and who is stupid, I think. Was that something like that? It might be God's mechanism. Okay, so how to build in practice. I know we've been here, so let's talk about this quickly. So we're going to say we have some distribution of degrees, and so we just make a whole bunch of these characters, and we say we have 30 of these and 12 of these and so on, right? And then we have a big soup of them, and we have to connect them up. And there are different ways to think about this, right? And you could say, well, let's just sort of choose nodes, like choose by nodes. But that's not going to work out well because you won't choose this one enough, right? So you really want to be in edge space, so we'll call these things stubs. and you want to choose a pair of stubs. So you randomly choose one, and then another one, and you just connect them up. Right? So it's a little connecty game. And you do that until you've everyone's connected. So this is the randomly select stubs, not the nodes. You have to have an even number. It's not a problem. You just sort of mess with it. Of course, if you started with so you could start with a real one and you've snipped them all, right? So you start with a real one and you cut all the edges, so they're all now in stubs, break it all apart, and then randomly reassemble it. Okay. Yeah. Okay, so you may accidentally get, this one might be chosen and then this one, so you'll get a self connection. You could get loops, so that's a loop. You may get these two joining to these two, so that's a double connection, and so on. So, and you may want that or not want that. So, and if you do, you can clean it up later on. And so these are problems. So, okay, we're just going to randomly rewire edges to clean these things up. So one reason is just to sort of get rid of these things, but there's a much better reason, which is to actually truly make a really random network that has a particular degree distribution. Okay, so we're going to take two edges that we find in the network. So we randomly find those, right? We just have a big edge list and we choose two of them at random. And then we look to make sure that they're not, connecting the same nodes or anything. And then we do this. We're going to just, and it could be either way, but we just swap one this way and swap one this way. So what happens is, if you look at each node, its degree stays the same, right? This is still a degree 3 node. This is still a degree 4 node, 3 node, and 4. So we're not destroying that. You can think of these as little cycles, on, off, and we're just clocking them around. And this has kind of held up as sort of the simplest thing that you could do that randomizes the network but preserves the degree distribution, right? So I1, if we do this over and over again, right, we're moving I1's links around, we're never going to take them away. So it's tempting, it's surely tempting to pick up an edge and just randomly put it somewhere else, right? But as soon as you do that, you start to destroy the number of friends nodes have, and in fact you'll make a soup and you'll get back to Poisson degree distributions, right? So if you just keep picking up edges and putting them down everywhere, that will happen. So you have to do something like this, a random rewiring, and because this one has lost a friend, you need to somehow randomly rewire someone else back up here, and this one's lost a friend, so you see that this is a little way to balance it. Right. So I remember I thought of this, and I was at Santa Fe with Duncan Watson. I said, "What about this?" And he said quite reasonably, he said, "Well, who knows? Like it could like mess things up in some other way." And then we're like, "Yeah, probably. That's not good." And then a couple of years, that's stupid. Anyway, so this is good. And so this is well done. So the heuristic is to do this about 10 times. So I don't know if this is built into things like network X and so on. It should be. I made ridiculous C codes to do it, but yeah. So there is. So if you just join up the stubs, don't worry about this too much, but basically that can lead to some problems, right? We can actually get some unusual, this is a pretty weird network. This is something where, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So you've got two nodes that have 10 friends, and then all of these others have 2. And you're going to randomly reconfigure. These are labeled nodes, right? This would be node 1, 2, 3, they're all labeled. It's going to be quite easy to, as you sort of connect up stubs, it's going to be easy to make this one and harder to generate this one. And that's sort of this little example. And this is a paper, I think it just lives in the archive. I'm not sure if it was ever quite published, but it was a nicely done thing. You can see that there's sort of this one weird one doesn't appear as much as it should. This is a ridiculous method that's like too exhaustive. We're not going to worry about it. But the switching one is the one I just showed you. So what you do is you match up stubs, and then you do this. You do the switching algorithm. Now, if you've got a real network in front of you already, you don't have to cut it up, right? You just randomize the edges. So you can just use this method from Uri-Alan and so on, right? You can just use this method straight away. All right, so this is a very nice thing. So now you can take a real network and make a whole ensemble of, you can make 10,000 networks that all have the same degree distribution but are otherwise randomized, right? And that's a good game. So that's, people have played this well. Okay, we don't have to worry about that. And this is the motif work. This has become a very well-used thing. The idea was they played around with the an E. coli network with actually not so many edges, of course, but you can see it's quite very, very sparse. But they did this thing of randomizing, taking this this gene expression network. They took this thing, randomized a whole bunch of times, and then looked at what was in the real one that seemed to be different from random. And so this is, they sort of famously got these three things out. The first one was these feed-forward loops, which is the kind of thing you find in opening an elevator or letting it close, right? So if X turns on, then that's going to start Y, and that's going to start Z, but Y has to turn on, right? So there's a delay in Z being turned on, and that's what this is, right? So X turns on, here's X turning on properly. So X turns on, Y ramps up, and then Z starts to get going. If X is only on for a little bit, Y starts, but Z doesn't really get going, right? So it requires it being on for a while, but as soon as you switch off X, then Z stops, right? So that's sort of this asymmetric on-off switch, which is, a good thing. So nature's produced this a lot, right? And we use it in our own electrical circuits. So that's a cool thing. And so, what they were able to do here is to say, let's look at every possible little collection of 3 nodes. And it's directed, so you count up all the possible things. And you look at the real one, the prevalence of certain kind of motifs in the real one versus what's in the randomized one, and you don't see this in the randomized ones relatively, right? The little z-score thing, blah, blah, blah. Very good. So that becomes hard, though, if you go to like groups of 4, 5, 6, you get a combinatorial explosion. There's work by Wiggins that tried to do that. Chris Wiggins is now the chief data scientist at the New York Times, and he's still at Columbia in the Data Science Institute there. So they found this, which is and they look for this, right? It's a master switch, X turns on, right? You don't find that in the randomized versions, and they didn't find these things either, which is just a mess, basically. But this is something where they looked for certain things, and that's fine, but it's not the same as an exhaustive piece. Okay, that's fine. Okay, that's good. So throw this way. Okay, so I know you've seen this, but this is a beautiful thing. Good. Okay, degree distribution is a big deal. Now, we have to be careful about this. This is a very important thing, right? So of course we're just choosing nodes, right? So we're going to our network or our ensemble of networks. We're choosing a node and looking at how many friends it has. When we think about spreading, and a lot of mechanics on networks, we really need to be looking at edges. And so we need to start thinking about what happens if we jump on a random edge and then randomly run along in one direction, right? And we hit a node. What's the number of friends or the degree of that node going to be like? All right, so this is a real cornerstone of a lot of work that comes afterwards. So we need to understand it. So we'll have P, Q, and R, right? So Q is going to be probably the node at the end of a randomly chosen edge has degree K, right? So we go to our network, we jump on an edge, and then we randomly choose it, flip a coin, we go this way, we hit a node, probably that has degree K, which includes the edge you're on, is going to be QK. And so this is an easy thing to derive from PK. It has to be proportional to, we'll probably find a node of degree K, but there are K ways to get to it, right? right? So if you think of your network, every node that has degree 3, now there are 3, it's going to be sampled threefold the rate that it would have been if you just sampled nodes, right? If you have a degree 30, there are 30 ways to get to that thing, so it's going to be 30 times what it was. So there's this linear piece that just pushes it up, and really beautifully, turns out to be the rich get richer phenomenon, right? So this works for provides the mechanism for scale-free network growth, or any of those sort of adjacent ones, because you can go and meet someone in a network, and then you start to meet their friends, and their friends will be different, right? Their friends will have more friends. And this is going to be, so right, we're going to take this degree distribution piece of k and then push it across a little bit because we're going to multiply it by k. So it's going to have a higher average degree. If we normalize it, simply divide, right, sum over, that's all this is. We're summing over this blob and dividing through, so that's our normalization. And if you look at the thing on the bottom, this of course is just the average degree, right? So you can write it in that way, so people often do that. Average degree on the bottom. All right. So, as I said, the rich get richer mechanism is just built into this selection process. It's just there for free. The work by Redner, I should go through that probably. Redner and Krapivsky, where they looked at k to a power. It's certainly a thing you can play around with, but it doesn't have a simple story like this. All right. Very nice. And so this is an explanation of these things, right? So this degree 6 one is going to probably have been 1/7 if you're just choosing by nodes. But now if we go to edges, and you can think of breaking it all up and then choosing stubs, right? Now it's got 6 ways of being chosen. Of course, there are 8 edges in this thing, so there are 16 stubs, so there are 6 divided by 16. That's the probability of getting to 6 divided by 16 is the probability of getting this guy. So that's this thing here. Now we're going to, for convenience, it's often useful to talk about what's the probability that node you run into has k other friends, right? This is just a simple shift, k other friends. And so that's going to be the R distribution. So it's the same as the Q distribution, but everything's been shifted, right? So the probability that we hit, so there are these guys, 1, 2, 3 here that have degree 1. So there's a 3 on 16 chance we get to one of those if we go along an edge. That's going to match up with R0, 3/16. R0 is the chance that we hit a node that has 0 other friends. And this one has 0 other friends. This one, we come in here, it has 5 other friends, right? So Q6 goes to R5, Q2 goes to R1, and Q3 goes to R2. That's all, just a little shift. It's just useful in some calculations. And you see it in the literature. So is that okay? So these are amplifications, right? 6/16, certainly, considerably greater than 1/7. So its standing has gone up if we think about this. All right, I think we can get through this piece. So, yeah. As was on the previous page, right? All these things. So you can just write it down. You want to say, probably that someone has 7 friends is the probability that they have 8 friends, and because you want it, 7 other friends, I should say, is the probability that you hit a node that has 8 friends. Fine. So it can be written out in the same way, or just a shift from the QK one. So then you talk about this, what's the expected number of friends? And this is this kind of somewhat famous thing now. I guess there's some, I mean, it depends if the network is weighted and all sorts of stuff like that. But the basic story for a flat network is clear. So we're going to use this notation. What's the average number of other friends that a randomly arrived at node has? So this is just normal distribution stuff, right? We're just trying to find the average of k with respect to this distribution R sub k. We'll put that in terms of pk itself. Yep. Okay, we're going to stuff this thing in, right? So again, right, it's the chance that you run into a node that has one more friend than the one we're thinking about. And the average degree that's just going to come out, that's here. There's a k equals 0 piece, so we can shift this. We'll make it k equals 1 on the subscript, or the index will start at 1. And then we have this little beast here, right, k plus 1. And if we want to do the right thing, right, so you can play around with this in different ways. You could see this as, yeah, that's okay. I guess we could just do that. Why have I done that? Okay. Yeah, so the issue is this is a pk plus 1, right? So if we're going to return something where we have means and variances in terms of the underlying degree distribution, right? We're trying to tie everything back to the underlying degree distribution. Then this k plus 1 is what we need to connect with. So this is good, but this is a k, so we can make that k plus 1 minus 1. That's what's happening here. Right, so we made it k plus 1 minus 1, right? This is still k, times k plus 1. And then that's equal to k plus 1 squared minus k plus 1. Right, so it's just a little bit of just doing things clearly. We want to make all the things the same. Yes, often what we do in math, make all the things the same. And that's pretty good. And then so we're going to shift let me clean that up later on, because there's something a bit not great about that, right? What am I doing wrong with this? So this is, what am I doing? What? No? Crazy person. I mean, I didn't need to do that. I didn't need to do that. Yeah?
They just added in, like, j equals 0 goes away. J equals 1 is where that's something.
That's all good, right? J equals 0, yeah. Right?
J equals 1 is k plus 1 being 2, which is
0 and 1 go away. So we're still good. Yeah, all right. So I didn't, because this would have been k equals 2,
yeah.
and then I just moved it down. Yeah. Yeah. It was just nice. Just, yeah. Okay, so, and then when it's back to j equals 0, then we're good, right? This really should be j equals 2, but of course we can shift it back down. So, yeah, okay. It's just, that wasn't very nice. Okay, so, so we have, what do we have? We have a j squared and a j, pj, so this is going to be the second moment minus the first moment. And we had this beast out the front. Okay, so I've just repeated up there. It's true for all random networks. This is not about degree distribution. For the standard random networks, then we have this piece, right? So we had this kind of, this is for Poisson degree distribution. We had the second moment is the first moment squared plus the first moment. So if we stick that in, we get this kind of funny result. So we're just going to stick it in here. This is the second moment. We're stuffing that in here. These things cancel. This cancels here. We get the mean back, right? So if you run along an edge in a Poisson degree distribution, degree distributed network, then you hit a node, it will have on average, the number of other friends we'll have will be the same as the number of friends that a randomly chosen node will have. And that's it. So that it's, right, so they'll have one more, right? So your friends will have one more friend than you on average, which is fine, but it just, because it's so tightly connected, it's so cleanly connected, can lead to some little mistakes in calculations, actually. Right, that's a property of this guy, so yes. Okay, so this is a special thing. I'm just going to get rid of this. Let's not worry about that. that's fine. So in fact, really what's happening is R sub k is equal to P sub k if you go through it. It's not just the average quantity. It's really the same. Okay, so why all this matters? So we'll finish things. I know I should have gone through this fast. So this is the number of friends that a node has. Yeah. So it's going to be, on average, you have this many friends. We'll go to a node and then look at all of its friends. And on average, this is how many other friends they have. So we're going to multiply those things together. These pieces cancel. And then we've got the second moment minus the first moment. So, right, so this is, you've got yourself, you've got your friends, and then your friends of friends. And so this is a measure of the the expected number of friends that you have, right? We're going to go to a node, and we're doing two things here, right? We're going to a node and getting its average, but then we're running along edges and getting the average for their other friends. So they give us these different pieces. So it's not just the first moment. You could expect this, right? You could say, I have on average this many friends. My friends will have on average that number minus 1, right? Because they're like me. Right? That would be the kind of naive thing to just write down, right? In this network, everyone has 7 friends on average. So the number of friends you should have would be, on average, 7 friends. They all should have 6 other friends. You think you'd do that. But actually, that's not true at all, right? And it depends on the second moment of that distribution. So if there's a large second moment, which is often true of these networks, then this thing can be large. Power law distributions, but friends are different from you. And yeah, this is a class size paradox thing. Okay, so if you go through, you can check that, in fact, the only way, this is just a little piece, you don't have to worry about it too much, but the only way that that your friends don't have more friends of you is everyone has the same number of friends, right? So it's only in that case. Yeah, fine, good. Right, so there's no variance. Everyone has the same number of friends. And so here's some work that's been around. So that's quite disturbing, right, for a start, right? I mean, I know we've talked about this, but if you've been in POCs. But your friends have more friends than you. But it's actually, there's been all sorts of elaboration. So now it's a generalized friendship paradox. And this is looking at, I think it was Google Scholar. Maybe they use something else. Friends have more co-authors, citations, and publications. It's pretty bad. There's on Twitter. Well, that's the butt thing, but it's still true. It sort of all makes sense. That's also a bad thing. Maybe so right. So no one's looked at the negatives, and hopefully this is also true, right? But this is, and I think it's such a sort of a beautiful result that in some ways, and it's just there for free, right? So the kind of keeping up with the Joneses feature of social phenomena is sort of just like the fact that we just exist in networks. It's there. You will just, if you survey your friends, and of course it presumes this kind of, everyone's weighted equally and so on, then you will be disappointed. But it depends how you react, right? So if everyone thinks, everyone's a little bit better, so we try to get better. So maybe that's sort of built-in indexing up or ratcheting up of social phenomena is sort of maybe there for free, which is an interesting thing. Okay, so this is all right. So I think we're about to finish. So, but this really matters in terms of this app, and I'll come back to this. But this just a little bit more to finish in the next piece. This average number of other friends really matters tremendously when you think about things spread. So that's going to be the next big deal. But anyway, so this is a bad result, maybe. But sort of a good thing perhaps for society. All right. Okay. I know we've been here before, but we kind of had to dig in again. So I hope that was okay. Thank you. So Tuesday, also office hours. Yes. Which got to just keep going, basically. All right. Escape. People, run away. All right. So I'm going to start off by finishing this section. Then I'll This is exciting. Come on. Yes. Okay, so I'm going to finish this little bit of what was a random network's nutshell, and then we're going to talk about generating functions, which is just a beautiful thing. Agreed? Yes. We'll have some fun with those. They allow us to do some really lovely things, thinking about all sorts of counting problems, especially what we're here with random networks. They can be somewhat obfuscatory, though, which is fine. You know, Fourier transforms and things, you go into another world and you sort of play around there and you come back. So there's some magicalness to them. And so we'll see that there are a couple of ways to get to things that, you know, we can use this generating function machinery, generating functionology, and it's very satisfying and beautiful, but we can also do some things in a very direct physical way. So there'll be a mixture, you know, this, and this sort of talks about the literature a little bit, which is a mixture itself. Okay, so, all right, so we went through a whole bunch of stuff about random networks, and I realized for many of you it was a recap, not everyone. Last thing we talked about was this business of your friends being strange, right? That framing, which is really the observation that if you jump on an edge and run along an edge and hit a node, then the degree distribution of that node will be not the underlying degree distribution, right? If you sample by nodes. So that's a really important distinction. And we'll see, we see that actually for Poisson degree distributions, which is every network basically, right? So if you walk up to this box and you pull one out and it's a large enough box, N and M are large enough, then you'll get one with a Poisson degree distribution, right? So you should, I mean, in some sense you might think, okay, let's just think about those guys, which is what we did for 50 years. But the real world doesn't have any of them, so that's a problem. But if you do that with those guys, then these two distributions, P sub k, which is the probability that a randomly selected node has degree k, and R sub k, which is the probability that a randomly arrived at node has k other friends, they're the same. That's just a feature of the Poisson degree distribution. They are the same distribution. It's not true in general. Okay. All right, so we're going to, and I said a lot of this is about contagion, so we're going to think a little bit, start talking a little bit about this before we get into generating functions. You know, this transition, really fundamental thing, phase transition, right? Nothing takes off, or there's no large macroscopic structure in this network, or we can, if it's a dynamic process, nothing is taking off. And then yes, right, so there's some big blob. And in fact, you know, for random networks, you only have to go out for standard random networks, average degree of four friends on average, then you get almost everyone is connected into this big blob, a giant component. All right. Okay. So we're just going to go through this, and then we'll have a little interlude. So this is one way to think about whether a giant component exists or not. So there's an existence thing, there's the size of it, there are a number of different levels that we can sort of tackle it. But the first thing is there a giant component or not? So lots of words, but basically if we're following a random edge, so we just choose random edge, we do this over and over again, and then if we travel along, we hit a node, and we look at how many other friends it has, and we do that again and again and again. If on average we see at least one other friend, then we're on average seeing exponential growth as we move through the network. And there may be many, many dead ends and so on, but we are seeing this kind of exponential growth, and that will simply just tell us that there is a giant component. And that's it. So this is a condition. It doesn't tell you how big it is, it just says it exists. So that's a good thing to start with. And so for the stuff we've developed so far, that means the average degree of this R distribution, which again is the number of other friends a randomly arrived at node has, if that's greater than 1, then we have a giant component. And so in terms of what we've established, and I don't expect you to remember this, but this is I'm going to say this is an opaque object, right? It's some stuff, you know, and there's no subscript here. This means that this is the second moment according to the underlying degree distribution. This is the first moment or the mean, and this is the mean again. Okay, so if that's greater than 1, then there's a giant component. So that's good. So we can be kind of happy we have like a little test, right? So someone gives you a piece of K. Yeah, let's do that. Right, so just once again, I think I should just write down. So yeah, We've got P sub k, and then R sub k is the probability that we hit a node of degree k plus 1, because we're interested in k other friends, right? K other friends. Think of it like that. And then we'd have to normalize it, and the normalization will turn out to be the average degree. Okay. So, just say again, it's got, as we move from the underlying degree distribution to this edge degree distribution, then we get this factor of a linear factor, right? So if we have a degree distribution, we multiply it by k, it's going to push it a little bit to the right. Okay. Fun times. All right, so second moment's a big deal, and this is this property that we talked about for the strangeness of friends. It's kind of a dangerous thing. So if you have a degree distribution that has some skew in it, and scale-free networks, right, which everyone is now arguing about 20 years later because it's a terrible thing to do. Anyway, heavy tail distributions, let's say, then this is potentially quite large. So, there's this odd thing because you are, if you have this big skewed distribution of degree, then as you wander around this network, you're going to hit some people with lots of friends. And then, of course, they have lots of friends. And then there's a good chance that they will hit people that have lots of friends. So it takes off. Anyway, so I'm going to say that this is true, but not useful. And, of course, you can play around with it. And you'll see in older papers this kind of thing. Or in books. You'll see this in books. People will write this down. This is also true. It's just a rearranging of this. Right? So you could say, okay, here's a test. I've got some P sub k. Find the second moment. Is it greater than the mean? Times 2, right? Fine. But that's not a very, it doesn't tell, there's not much of a story there, right? It's just a little mathematical test. Okay. So a couple of things then. We know we have this local branching structure, right? That was a sort of observation. There's no clustering. And we're, of course, thinking about infinite random networks. And it's always, almost everything with, well, it's not true, but a lot of dynamic things, certainly for networks, it's better to think about what happens with edges, sort of live in edge space. It's just, you'll get a lot further. So, very simple thing, if we think about something spreading, right, and we infect this node, and it has Ebola, whatever it has, or believes something about, a political figure, then it's going to start spouting these things off to its friends. And if it doesn't take, then they're not going to repeat it, right? So that's a very simple mechanism. And so it's a binary case. You're either infected or not. So can global spreading occur from a single seed? This is a very fundamental question. We want to ask this. And then you start thinking about, well, what if we had a group being infected or a distributed set of seeds? And, you may be trying to change the world by educating people or making them buy your toothbrush that's made out of bamboo or something, so good and bad situation here. A lot of the work that's been done in Silicon Valley in the 2000s has been towards making you buy things and stay attached to things. So thank you. The best of the generation has been working out how to sell ads. It's great. So this is a way that I like to frame it. It fits with a lot of different things, but I'll have a particular notation. We had, if you're in POX, there's R0 is the reproduction number for, and you've maybe seen it somewhere else, for the famous spreading models, SIR type models for diseases. So we're going to call this thing the gain ratio. It's going to be this R, average number of infected edges that one random infected edge begets, right? Infected edge. It's going to hit someone, there's some disease spreading mechanism that takes place, whether it takes or not, and then on average you do this over and over and again. All right, and then we'll have a couple of things. So, all right, well, let's just encode our mechanism with this probability, BK1. So it's this kind of one-off thing. It could be that there's an infected edge coming into a node, there's some clock, and maybe what we think about is over, a long period of time, what's the probability that this one gets infected because it's still being hammered? Or it could be just this one-shot thing.
whatever we want to do, we can collapse it down and say we've got this these quantities BK1. There's a reason for having a 1 here, so this means that one of your friends is infected. You've got K friends, one is infected. What's the probability you become infected? So these are vulnerable nodes if they're infected, right? These are the ones that are easily tipped. Yeah. So we'll just build out a simple story for this, and we'll get what I think is a much better way of looking at these. It's various names for it, right? The giant component condition, or if we're thinking about a thing spreading, it's a cascade condition, a global spreading event condition, whatever. Okay. So we're actually going to go back to QK. QK was that sort of intermediate one, which is probably that if we run along an edge, we hit a node that has degree K, right? So it was P, Q, and R. All right, but this is a good solid object derived from P sub K, right? K ways to get to a degree K node. Okay, and then this is the correct normalization. So this is the probability that you connect to a degree K node. This is the number of outgoing infected edges, if it's infected, and then this is the probability of infection. So we've got 3 components we can break it down into, right? So this is structural, right? It's random, but this is a structural aspect. It's like, what's the probability that you hit a degree K node? Then this is completely structural. In that case, it will have K minus 1 new edges that it would be infected, and that's if this is true. Now, just to sort of complete everything, this is again the probability that you hit that same degree node. There will be 0 outgoing ones if it fails, right? We could easily have just sort of written this down, but this is now we've accounted for all possible things that happen, okay? And 0 has this nice property of multiplying things and making other things 0, so that always goes away. Okay, good. How do we feel about that? Thing is, you can read off what's going on here. This is actually the same condition that we had before, right? We just want this thing to be greater than 1. It's what we had before, which was the second moment minus the first moment divided by the first moment, which was a bit of a obscure thing, my view. You can see this, so we could generalize from here, right? This could be a correlated network and all sorts of crazy things. So this, whatever needs to go in there, could go in there, and then you could have edges of different flavors, so we could talk about which ones are going out, right? It could be the ones that are green or the ones that are directed or whatever. They could be infected. You know, and this could be a much more elaborate thing. But we could just sort of expand these things, and we'll always have these 3 pieces. In fact, that's something we've done with papers, which is, you know, too much probably. But anyway, okay, I'll put these big fun dots in there just to show you there are these 3 pieces. Boom, 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 greater than 1. So that retrieves our thing, but it's better to just leave it in this case, right? So we could, as you saw, you know, rearrange all of this and end up with second moment is greater than 2 times the first moment. People do this all the time, and in fact, you get to that result if you've come from something more general. Maybe you're finding, you know, like a largest eigenvalue or something, like you're doing some other kind of calculation. You've done something more sophisticated, and then you get to this condition, but you have no physical intuition for it. You have the correct mathematical expression. All right. Exciting, right? Okay, I think it's good. You know, it's good to understand things. So this tells the story, basically, as we line it up, and we're always going to keep this order and keep them separate. Okay, so rampant spreading would be everyone just gets hit, right? And this is actually just the condition for a giant component, because we're not even thinking about a real spreading mechanism anymore. We're just going to, like, if you sort of drip it in, you know, add an infectious agent somewhere in the network, and it just permeates everywhere like a liquid. And then we do that over and over again, and we see if we have a giant component. So this all collapses, right? We have a 1 here, and then we get back to this. So this is the giant component condition, I guess. Yeah, this was a slight generalization to have an infection probability in there. Okay, second moment minus the first moment divided by the first moment, right? So there we go. So that's a good thing. Simple disease would be just there's this kind of one-off probability. That's fine. You know, this is just a piece in here. So you can imagine this is what's happening on this network. So there's just a fraction. We could actually beforehand just go to every edge and take them out with probability 1 minus beta. So that's an edge percolation, a bond percolation kind of thing, right? So percolation we talked about in POX, right? There's nice things, and usually in 2D we played around with that sort of thing. But of course, any lattice you want, any dimension you want, and of course you can do it on networks. Okay, so the critical value gets increased, right? Because the network has been pared down, so it had to be more connected to start with for things to spread. Right, so we think of beta, right? As beta goes to 0, you are taking all the networks, all the edges out. So the chance of a giant component goes down unless it was super connected to start with. Say the right things. Bond percolation. And then if you want, you can figure out the degree distribution, right? So this is the underlying degree distribution. It's a nice little calculation to figure out that this is the resulting work. So because what can happen is, if you have in this new network, a node with degree k could have been a node that had degree k, k plus 1, k plus 2, k plus, right? It could have had any higher degree, and it's lost the right number of friends. And that's what this is, the failures. Okay. How do we feel about that exciting thing? Anyway, this is tidy. It has a physical story built into it. It's good. Good thing. All right. Proceed? Yes. Okay. Yeah. All right. Okay, so standard random networks, right? The ones that we get if we just rummage around in this box and we pull one out, the Poisson degree distributed ones, which don't exist in the real world, but kind of very important things. So there's this interesting little calculation. So the second moment is the first moment squared plus the first moment property of a Poisson degree distribution. So we can go back and stick it into our giant component condition. That's our second moment. We're going to put it in here. So you'll see that these two will cancel. We're going to have the first moment squared divided by the first moment, and we just get the first moment of that. And so this is a result we've talked about before, and it's in the plot I keep showing you. But yeah, if the average degree is greater than 1, then we have a giant component. All components are finite. Yeah, okay. Phase transition, great. And so it's a critical point of the system. Okay, so that's a good thing. All right, very good. Okay, but again, that's just in this is only for, I mean, it's weird. It's for basically all networks, but they don't exist in the real world. Okay, right. Poisson degree distributed networks. If we have something like this, let's imagine that this really is a crazy argument right now. We talked about it yesterday in the paper shredder, the paper that scale-free networks are rare. A pretty shreddable paper. Okay, so let's imagine we have a, we have a nice degree distribution. We're going to say gamma is between 2 and 3 because that's exciting, right? That's the small mean, relatively small mean, but large variance. And if we have no upper bound, then boom, it's got an infinite variance. It's all great. K is just greater than or equal 1. So the second moment is going to be this beast, and we're going to approximate this, right? So we're trying to find this is just a normalization constant. So we're just trying to find the average of this K squared, second moment, which we can approximate this. We make a rough thing. So this is x to the 2 minus gamma. And we're just going to integrate from x to infinity, 1 to infinity. This is a standard integral. This is very simple. That goes pop, right? Because gamma is between 2 and 3. Exactly what we were saying. So that's a lot larger than the average degree. And as a result, there's a giant component. Always exists for these kinds of networks, right? There's no... Well, for those gamma between 2 and 3, boom, we've always got one. And so this became a massive result. I need to put it in here properly. Let's see if we can find it. That's fun. Vespaniani. So Vespignani, who's at the Networks Institute now in Northeastern, at Northeastern. Let's do this, Google Scholar for Vespignani. And Roman Pastor-Sartoris, who was a postdoc in my group. And so this is his most cited paper. It's, Ramu here. And that's exactly what it was. It was basically really just noting that these things have an infinite variance. And if you look up the calculation they've done, it's in fact not about networks. It's all framed in that way, but it's actually, they've done an approximation, which means that they're doing a contact rate thing. So instead of anyone having someone has a degree 7, it really is they connect with 7 other nodes in a time step, and then 7 other nodes, right? It's not fixed. That changes things by a little bit. It's not a big deal, but that was a bit confusing for people. Yeah, he's done well in general, as you can see. It's hilarious. H-index of 96. So again, 96 papers with that, at least 96 citations. Okay, but yeah, if you look at this, lots of spreading stuff. And he spent more of his work, though, in the last, sorry if that's too small, 10 years has really been about disease spreading. Okay, yeah, cool. This is the airline transportation network, so they actually have data. Vittoria Colizza, she's very nice, did a good job with this. Basically, it's not good. You would have to take out like at least 95% of the flights to make the human safe. But it's not good. Yeah. Meanwhile, nature's experimentally making new flus and Ebolas and yeah. Okay. Oh, that's interesting. Yeah, so you could try something really simple like everyone has the same degree, right? So, you can calculate, it's not too hard to calculate, but is it degree 3 or degree 4, degree 5? Degree 3 that's a lot of mixing, right? So in fact, so degree 2, if everyone has degree 2, then you sort of might get a long ring, but right, that's what it would have to be, but that's a thin thing, that's not gonna work out. But degree 3 is, you have all these things connecting up, you gotta make a big mush with that one. And it's going to be hard for them to be little, right? So you'd have to have maybe like a bunch of them connect together, but then close off and not be connected to anyone else, right? If you're randomly linking things up, that's impossible. So that's good to know. Okay, so this is something. So I'm going to show you a calculation that goes wrong, principally because of this this fact that Poisson degree distributions give rise to P of k equals R of k, right? That's a weird feature of them. So we've had this notation. S1 is going to be the fractional size of the largest component. I guess I should say fractional size. So we're going to have our Edish-Renyi network, infinite 1. So let's do something sneaky because we've got envelopes floating around. No, we don't. But yeah, we don't anymore. I guess your iPad, right? Napkins. People still use napkins, right? Maybe? Was that gone too? You millennials? You just text your napkins to yourself. It's like with the doorbells. Even saying doorbell is threatening. Okay, so let's say, let's sort of make this little gamey thing. We're going to say that probably the randomly chosen node does not belong to the largest component. Okay, and then maybe we can make a little iterative thing. This will be the essence of a whole set of calculations that one can do, and we'll do a few of them. But the idea will be there, right? So if we figure this out, then this will have to be 1 minus the fractional size of the largest component, right? So this is a probability. You can think of it as probability and size matching up. It's the probability that you're not in the thing. So here's our little trick. So if a node is not part of the largest component, then none of its neighbors can be, right? That would be So we can, and then because we've got randomness, we can think, well, maybe we can make a little recursive calculation. We don't have to like go out to 2 neighbors and 3 neighbors. It's just one set will work. So this would have to be true, right? So the probability that a node is not connected, well, it can have degrees, going from 0 to infinity, so we allow all that. And if it's got degree 7, then we'd have to have all of its 7 friends are not in the thing as well. So that happens with this probability, delta to the 7. And then we sum over all of them. Sort of seems okay. I mean, right? It's not a bad argument. So you can easily be led in this way, and people have sort of put this in papers and books. Maybe they knew what they were doing, but the thing is, this can't be the same delta, right? This is the probability that we choose a node, and this is the probability that we choose a node by its edge. So this is your friends are strange. So this is not acknowledging that your friends are strange. But it all feels good while you're doing it. No one wants to believe that, it's solvable. This is pretty cool. Also, very disappointingly, it works. So we're going to put it in a Poisson degree distribution. All right, we're going to stick it in. This is the good old thing. And again, every network pretty much that we pull out of here will have this. So that feels good. We've got a k factorial, delta to the k. Here's our actual powers of k, right? These are constants. I know this notation could be confusing, but these are constants. This blob can come out, so let's do that. So the e to the minus, the mean comes out, and then we're going to schnook these things up next to each other. Average degree and delta, they're both the power of k, so we'll make them friends. And we've got a k factorial on the bottom. So this is blob to the k over k factorial. It's just a beautiful thing, right? It's exponential. So we've got e to the blob, and it's e to this blob, which is the average degree delta. So this is all pretty enjoyable. We can factor out that average degree. So we've got and we'll do it like this, e to the minus average degree. And putting the minus sign out here is, this is a hygienic thing to do, right? Because 1 minus delta is manifestly, that's positive. This is a probability. So this is a positive blob, this is a positive blob, so we sort of obliged to put a negative there. I can't tell you how important that is. People really don't do this much, but you just really, 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 really should do this in a nice way. Yeah, right? Whenever you have things you know what sign they are, make it clear. Okay, so then we have this point that the probability that a node is not in the giant component is really 1 minus the fractional size. So we could stick all of that in. That 1 minus delta there is actually just the fractional size, so that's this piece. And then on the left-hand side we have delta, so it's 1 minus the fractional size. So I put it in there, right? So I put in 1 minus the fractional size here, and then you have to multiply it through by a negative if you want, and then swap the 1 over to the other side, and you get this. So that's pretty good. So now we've got a thing where we can tune this average degree, and we'll get the size of the giant component. Which is this is an achievement beyond what we had before, right? This is the actual size of it, not just whether it exists or not. Now, whether it exists or not is not kind of obvious in that, though, right? You have to sort of play around with this a little bit. It exists if this is greater than 0, right? So we'd have to kind of solve this thing. A little tricky to solve this character, but actually there's only 1 average degree in here, so we can unravel this thing and get average degree as a function of size, right? So we're trying to get to this. Yeah, we're trying to get to this blob. Well, we're trying to get this thing, right? Average degree is this way, and this is S1. But we can plot k equals some function of, we've actually got this. So this is doable. Fair? All right, so you could actually put it into a thing and plot it. You're right. You open up math. I'm kidding. You don't use Mathematica, right? No one uses that. Wolfram. Use Python, I guess you do, right? And then so you can make it, and it'll be fine. Right? Okay, good. So there's some limits. You could do some things like this. So this is the rewriting piece, right? So undo the whole thing. It's an interesting little blob to look at. So it looks a bit nasty, right? So when S1 goes to 0, this goes pop, and this also is log of 0. So, you know, be a little careful with that. This is going to be good, right? So it's average. First of all, we can sort of look at two of these, right? So the average degree goes to 0, so no one's connected to anyone else. Then this goes to 1 minus 1, right? 1 minus e to the 0, doesn't matter what this is. This is always something between 0 and 1. So there's going to be 1 minus 1, so it's 0. So it's just looking at this. So that's good, that makes sense. As it goes to infinity, again, this is good news, right? This will go to 0, and we'll get to 1, so that's good. You can see, depending on how you want to play around with this, right, you could do some derivatives and things, but basically there's a critical point when average degree is 1. And, right, so it's only solvable, so this is where you get to the point. So you only get this solution, a positive solution, when the average degree is greater than 1. You know, it just takes a little bit of playing around with. But you can think of it as some sort of transcritical bifurcation. That there are a couple of solutions, and the way to think of them, this is always very, very pleasant, right? There's actually kind of another one here and another one here. And it's transcritical because these two things swap. I mean, maybe I'm overstating things there a little bit, but that's often how these phase transitions come out mathematically, right? So there's actually, this really is a curve that keeps going. It doesn't go boink like that. It's just that these things cross. Coolio? I know. It's really nice. Okay. Yeah, maybe. All right, good. So, right, so we've got everything. And I said dash, 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 dash. Good. So that little calculation, this sneaky little thing, right, where we say delta equals, yeah, it totally works. You know, you can run your simulations and this matches up perfectly. So you leave, right? You just close the book. But it's totally wrong. So, and the reason is that those two deltas are the same only for Poisson degree distributed networks. Right? So, I mean, I've said it out loud. This is exactly the thing. So we know our friends are different. So it works because the average degree of a node randomly selected is the same as the average number of other friends of a node that's randomly selected by running along an edge. So we need another one. We need a delta prime, actually. Right? We need something else. So we need to do something like, and really, so this will be the smart thing to do. We need some, and I'll just bash some things here. So we need to have delta equals the sum from k equals 0 to infinity. It would have to be pk, and then it would be, did I say, yeah, just delta prime to the k. Right, so delta prime is the probability that if you run along an edge, you reach a node that's not part of the network, the giant component. Really, you find a recursive story is for the delta primes. Right, so if you hit a node, what's the chance? And that's the kind of mathematical thing we'll get to, right? So you don't start at a node, you just run along an edge and think about what the other edges are like coming out of the node you hit. You can get a consistent recursive story for that, because you know the edge story stays the same, right? The probability that this edge leads is this friend has a certain other number of other friends. That's the same as the edges coming out, right? There's no the words. If you randomly select a node, and you randomly select a node by following an edge, these are different things, but here we're going to randomly select a node by following along an edge, and then we're going to do it again. And so we're doing the same thing, right? We're really doing the same thing. So that's why that works. So what you do is you solve this problem for delta prime and then just sort of stick it back in here. That's the idea. And this could go on forever, and I'll try not to make it go on forever, but it's really it's really a fundamental thing. Okay. So generating functionology. which some of you will have played with. Yes, a little bit. If you're a combinatorics fan, you will have seen it, but you don't have to worry about it too much. There really is literally, I mean, I'm not just making this up. I'm very pleased this exists, but this is Wilf's book is truly called Generating Functionology, and is a charming thing to look through. Okay. All right. Too much pain? Not enough? Okay. All right.